Again, welcome to Biostatistics 1. In our previous lectures, we covered a simple linear regression. And we said that a simple linear regression normally have only one independent variable. So we are going to have only one variable that will determine our dependent variable. So an example would be, is smoking causes lung cancer? So here we're dealing with only smoking, one variable, smoke, causes lung cancer, which is the dependent variable. Now, in multiple linear regression, we may have more than one factor. For example, we go back to the smoking again. We can say, okay, smoking and also good nutrition causes lung cancer, or smoking, good nutrition, and exercise, less exercise causes. So what we're trying to say is that in simple linear regression, only one independent variable will determine the dependent variable. In multiple linear regression, we are going to have more than one independent variable. So we may have two or more factors. So our main objective is to, again, go through the general idea of both simple linear regression and also multiple linear regression. Again, our model here is linear, a straight line, linear. We also have, for example, a logistic regression, which is nonlinear. We may have a exponential, a logarithm, etc. We're also going to talk about categorical explanatory variables. We know regression normally deal with quantitative data. So because we know the model is a straight line, it's an equation. But sometimes also we can convert a categorical data set, such as yes, no, convert it to a quantitative so that we can do again a regression model. We're also going to discuss about regression coefficients. Also, we're going to examine multiple regression conditions. And the conditions under multiple regression is the same as simple regression also. And we may also discuss that. So first, the general idea, let's go back to simple regression. We said in simple regression, we may have only one independent variable, or we also use the term explanatory variable. And this will be X. So S will determine our Y. So example, smoking causes lung cancer. Or is there any relationship between smoking and lung cancer? So again, simple regression, we have only one independent variable that will determine one dependent variable. So we assume X is our independent variable, Y is our dependent variable. Now, in multiple regression, we are going to consider more than one independent variable. So example here, consider relation between multiple explanatory variables such as S1, S2 up to Sk. So it can be any amount of independent variable. And the response variable, which is our dependent variable Y. So in multiple regression here, we have variables, independent variable S1, S2 up to Sk, and they are going to determine Y. So example, smoking, good bad nutrition, less exercise can cause a lung cancer. So again, multiple regression model will help us to adjust the effect of confounding factors. Confounding factors, or even we have the term confounding variable. In simple regression, we have only one independent variable determine the dependent variable or determine the output. With multiple regression, we have more than one independent variable. So here we can even find what we call the confounding factors, and we can even adjust it. A very simple example of what is a confounding factor is, let's say in Florida during the summertime, and shark attack increases. There's high shark attack rate. At the same time, ice cream sales also increase in the summertime. So here we can see that there's a relationship between sales of ice cream and also shark attack during the summer in Florida. But we cannot say that, okay, when I get shark attack, I'm going to buy ice cream. No, that will not be the cause. But we have a common variable here, or a common factor, which will be the temperature. So we know that when the temperature of the weather increases, shark attack increases, and also the sales of ice cream increase. So that's the concept of confounding factors. So multiple regression have a very good advantage over simple regression when it comes to adjusting the confounding factors. For example, we know smoking causes lung cancer, but not everybody that smokes cigarettes have a lung cancer. Maybe the age can be an effect. The older people smoke for so many years, so they have the lung cancer. And the younger, maybe I start smoking, a teenager less than 6 months, and most of them doesn't have no lung cancer. So we can say that smoking and lung cancer, age also can be a confounding factor there. So also simple linear concept unit 14, our previous must be mastered before tackling the multiple regression. So again, our unit 14 was the previous lectures. This is unit 15, multiple regression. So the concept of simple regression and multiple regression, they are almost the same. As we said, the difference is that in multiple regression, we have more than one independent variable or explanatory variable. So this is an example of what we went through previous. Simple regression model, we have only one input, which is our x independent variable. So x can determine y. So here we say y given x. We are looking for our dependent variable y. When we know our dependent variable x, it will be alpha plus beta x. Again, alpha represents the y-intercept, or here we call it the intercept parameter. Then y given x, beta here will represent our slope. So this is what again we cover in previous lectures. Now to estimate for the model, we normally try our best to minimize the sum of residual square. Residual, we discussed that is the error between or the difference between the actual y value and also the predicted y value. So our goal is to reduce it. Because if some square residual is very high, it means we have a high error in our model, because residual again is the difference between the actual y value and also the predicted. So if we can predict correctly, then the residual will be 0. So our goal is to again reduce it. We also have the standard error. And the standard error again is that here we are going to use the formula square root of sum residual square divided by degree of freedom for the sample. So again, this is our new topic, multiple regression model. So here we can see our equation, y given two variables now. What is our independent variable y given S1 and S2? So it will be the y-intercept again plus B1 S1. Again, each independent variable will have its own slope. So here we have B1 S1 plus B2 S2, or beta 1 S1 plus beta 2 S2. Now, if the input is 3 S1 S2 S3, then it will be alpha plus beta 1 S1 plus beta 2 S2 plus beta 3 S3. So again, y given S1 S2 is the expected value of y given the values S1 and S2. Then we have the alpha to be the intercept parameter. Then we have the beta 1 is the slope for the parameter S1. Beta 2 is the slope for parameter S2. Now, if I have the third beta 3, S3, then it will be beta 3 is the slope for parameter S3. So the equation here means we have two independent variables, S1 and S2, that will determine our Y, or the expected value of Y given S1 and S2. So to estimate for the coefficient, our goal again is the same as the simple linear regression. We need a model that will minimize again the sum residual square. So again, Y caret means our predicted Y value. We want our predicted Y value should be close to the actual Y value in order to minimize the sum residual square. Again, residual means the difference of the predicted value and the actual value of Y. So that would be something like an error. We also have the standard error of the regression. Remember, we studied the standard error as the standard deviation of the sample. So here we say standard error of the regression normally will quantifies the variability around the regression plane. And to find it is the square root of sum residual square divided by degree of freedom. So in the regression modeling, we said a simple regression model that fits in a line with two-dimensional space. So that's a simple regression. Why is two-dimensional space? Because we have only one input, X, and we have one output, Y. So it's only two variables. So a simple regression model will always fit in a line in two-dimensional space. But a multiple regression model with two, here in this case we say with only two independent variables, will fit regression plane in a three-dimensional space. Because here we have only two independent variables plus the Y, or the dependent variable. So in simple regression, we have one independent variable and also we have one dependent variable. So it's two-dimension. With multiple regression model, a minimum of at least two independent variable is needed, and also the Y, our dependent variable. So always it will fit in a three-dimensional space. And actually in a real world, especially for example in data mining or data science concept, we have an algorithm called a support vector machine. Support vector machine concept is almost the same as regression, but in support vector machine, we may have a infinity number of independent variables. A very good example would be the computational biology, like a gene or DNA data set. Especially gene, we may have over 5,000 dimension, independent variable 5,000. There's no way we can be able to use regression for that. So there's an algorithm called support vector machine, which basically make it possible for us to create a model based on infinity number of dimension inputs. In our course here, we're going to study only the two-dimension, which is the simple regression model for chapter 14. Then multiple regression, we only go up to three-dimension, which means we have two independent variable and one dependent variable. Also here we said that the multiple regression model with k explanatory variables, which means with k number of inputs or independent variables, will fit in a regression surface as k plus 1. So that's why we say three-dimension, because we have two inputs and then we have one output, so it will be 2 plus 1. So this is how it looks like, three-dimension. We can see we have the x1, we have x2. Now x1 line will be determined by its slope. So this is B1 or beta 1. That is the slope for input of S1 or independent variable S1. So the slope will determine the steepness of the line. Then when we look at the S2, second independent variable, and the slope of it also will give us the steepness of the line at beta 2. So the dimension of the the effect of the three-dimension plane here will be determined by the slope of both S1 and S2. So here we have the response plane. Then we have the observational YI. Again, this is we can see the intercept. This is a Y. So where the X, or say S1 slope line touches the Y-axis, and also B touches the Y-axis, that will be our Y-intercept. The concept of Y-intercept is what is the value of Y when X is 0. So on the Y line, S1 and S2 value will be 0 here. So let's go through the interpretation of coefficients. Here we say the model with 2 independent variables, which we saw in the previous slide. The intercept, again, the intercept will predict where the regression plane crosses the y-axis. We saw that here. So where the plane, we can see the x1, x2, where the plane crosses the y-axis, we give us the intercept, or sometimes we use the term y-intercept. So we say again, the intercept predicts where the regression plane crosses the y-axis. And also the slope for S1 only predicts the change in y per S1, holding the S2 constant. Now the same thing for the slope for S2 will predict the change in y per unit S2, and it will hold also the S1 constant. So we say the slope for the S2 predict the change in y per S2 unit, holding the S1 constant. So next we move to the categorical explanatory variables in regression model. As we said, based on the regression model, we can only use the quantitative data, because in our equation we have a plus and minus. So there's no way we can say yes plus no equal to, we can't have two nominal values or categorical value. So normally when we have a categorical data, we try to convert it to quantitative or ratio, so that we can be able to do arithmetic operation. So example given here, we have a categorical explanatory, which is our independent variable that can be fit into a regression model by doing what? Converting them. So here, the example here, we're going to convert them to 0 and 1 indicator variables, which we call the dummy variable. So for binary variables, a binary variable means we have only two options. So for a binary variable such as yes or no, we can say, okay, we are going to represent no as 0, yes as 1. Because again, regression model normally uses quantitative data, doesn't use nominal or categorical data. Now for categorical variable with k categories, we are going to use k-1 dummy variables. So let's see an example here. So in this example, we have a variable named smoke2, which has 3 levels. Initially, we code 0. 0 stands for non-smokers, and then 1 is former smokers, and 2 is current smokers. So in order to use this variable in the regression model, we're going to convert it into a 2 dummy variable as follows. We have dummy 1, dummy 2. So when we see 0, it means non-smokers. When it's 1, it means former smokers. When we have 2, it means current smokers. So to come up with the regression model, if this is our data set, again, these are the values we are going to use. So we have an example here for a childhood respiratory health survey. And here we say a binary explanatory variable smoke. So this time the variable smoke is binary, which means you have only 2 possible values. 0 for non-smokers, and 1 for smokers. So the response variable forced expiratory volume will normally be measured in liters per second. So this will be a value. Now we assume a data set is given to us, and based on this data set of patients, we find the mean of the forced expiratory volume for non-smokers to be 2.566. Now we find the mean for, again, forced expiratory volume in smokers to be 3.277. Here we are assuming we know how to find the mean. So the mean basically, since the FEV is measured in liters per second, we may have maybe a patient is 20 liters per second, another one 45 liters per second. So we may have the data set. All we need to do, add all the data set, then divide by the number of patients we have. So that's what we came up with these two values here. Now, the regression model will be applied using FEV as our dependent variable. Then smoke will be our dependent variable. So again, let's go back for the example here. So as we said earlier, again, we have an example for childhood respiratory health survey. So we have a binary explanatory variable, which is called smoke. It's binary because we have only two possible values, 0 for non-smokers and 1 for smokers. Now the response variable forced expiratory volume is measured in liters per second. And we have the mean value for non-smokers to be 2.566. Then we have the mean value for forced expiratory volume in smokers to be 3.277. So here we can get our regression model. In this regression model, we are going to have our dependent variable as the FEV and independent variable is smoke. But the smoke has two options, as we saw, either for non-smokers or for smokers. So the least square regression line is given to us. Again, if we are using Excel or SPSS, we can easily generate this equation. So the intercept will be 2.566. And again, the slope will be 0.711. Now we can get our t-stat if we are doing a hypothesis. So we find the t-stat to be 6.464 with the degree of freedom here is 652 because the sample size is 653 minus 1. So we can find a 95% confidence interval for the slope, which will be 0.495 to 0.927. So this is the graph. So here we have smoke, non-smokers zeros, and then 1 is for smokers. So we can see the measure of the FEV, which is vertical, for non-smokers is higher than smokers. 1. Now, if we are coming up with this model, this will be our regression line, the most fitted place from non-smokers to the most fitted place of smokers. Now, most of the time, the regression calculations or problems, we solve it using computers. Because again, it's a very long process to use your hand, even in Unit 14. Unit 14, we have only one dependent variable. Now, when we have two or more, we are going to do twice of the work previously. So always we use computers solving this problem. So is there any confounding on our example? Yes, according to the research, age is a confounding. Why? We are doing smoking causes FEV, but we find out that the young smokers don't have this problem. The older smokers have it. So age can be another association. So here we say in our example, the children who smoke had higher mean FEV than children who do not smoke. How can this be true given that we know about the deleterious respiratory effect of smoking? Now, the answer lies in the fact that smokers were older than non-smokers. So age confounding the relationship between smoke and FEV. So a multiple regression model can adjust for age in this situation. So normally, again, multiple regression, we can use, this is an SPSS. So we load our data. This is all the possible variables in our data. Now we want to see if there's any relationship between smoke and age and also FEV. So you can see our dependent variable, we select FEV, then our independent variable only two, the smoking and age. Now we can add a sex to it if we want to know if there's any effect based on the sex. So if it is two, then we click OK. Then again, SPSS will give us the result. Or we can click on statistics. If, for example, we want to find the mean, standard deviation, other values, other statistics, characteristics values. Or if we want to plot a chart based on our variables we have, we click on plots, and we select the type of chart we want to again. So when we click run, this is our output for SPSS. Remember, our independent variable we selected was smoke and age. And our dependent variable is FEV. So SPSS will generate our slope, intercept, everything for us. So first, this is the intercept. Then we have the slope for smoking and also the slope for age. So we are using two variables, smoke and age. So if this is the case, then this will be our model. The intercept is 0.367. So it's 0.367 plus our first the independent variable, the slope is negative 0.209. So it will be negative 0.209 times smoke. So we have plus negative 0.209 times smoke. Then plus the last one. The last one is 0.231 times the age. So 0.321 times the age. So this is the model that we generate from the system, again using SPSS. SPSS is very straightforward. This will take a few minutes. First thing we need to do in SPSS, or in any data analysis software, is to load your data. So here I load my data and I want to do a linear regression. I select more than one very independent variable. So I'm doing linear multiple regression. I want to see if there's a relationship between smoke, age, with our dependent variable or the output to be FEV, forced expiratory. So this is our result, and we're able to generate this model. So what this result meant is that first we know the slope for the smoke is negative 0.206. So here we say that the slope coefficient associated for smoke is negative 0.206. This will suggest that smokers have 0.206 or 20.6% less FEV on average comparing to non-smokers. Now the slope for age is 0.231, suggesting that each year of age is associated with an increase of 23.1% FEV units on average after we are adjusting for smoking. So we can see that the smoke have more effect, and then the age have more effect, smoke have less. So we also can do the inference about the coefficient. So we can do our hypothesis testing also. Remember, we are doing regression, same as unit 14, simple linear regression hypothesis testing. Since this is a linear straight line, the only value that will determine the shape of the line or the steepness of the line is the slope. So we have to test the slope. So we have B1 equal to 0. This means we're testing the slope for smoke. And we also have to do the same thing for age. So using SPSS, we get the t-stat to be negative 2.588, and the p-value will give me 0.010. Again, we can follow the steps, same as unit 14. Get the HO and HA, find the t-stat using the formula. Then you have to find the SC also, because we use the SC in the formula. Then after that, if you know the t-stat, we can get the P from our table, T table. Then from there, we make our decision. Now, we can see using the SPSS, we were able to get the slope for smoke and also for age is here. And their standard error. And with the significant level is 0.010, the t-value we were able to find to be negative 2.588. And in this case, again, here when we are doing simple linear regression, the degree of freedom will be n minus 2 or n minus 1 minus 1. Here, multiple regression, k can be any amount. Here, right now, we have 2 because k represents the number of independent variables 2. So it will be n minus 2 minus 1, which will give me 654 minus 2 minus 1, which give me 651. Then inference about the coefficient, we say that using a 95% confidence interval for this slope, we get these values here. The lower bound will be 0.368, the upper bound will be 0.050. Both of them are negative values. So the last section will be examine the regression conditions, same as simple, this is linear, same as simple linear regression. We need to consider the linearity, independency, the input, normality, and also equal variance. And this also depends on the residual analysis of the sum square residual. So this will be our conclusion of multiple regression. We will try and have a note and make a lectures on how to use the SPSS on it, and also went through how to use Excel for simple linear regression. We can use Excel also for multiple regression, but the problem is that we have to have a special hard-on features for Excel. So I have a basic Excel program which doesn't come with any hard-on features, but I can also do a simple linear regression with it. So my next lectures, again, to be a very short lectures, how do we do regression using or generate the regression model using Excel and hopefully SPSS also. So again, wish everybody the best and see you in the next lectures. Thank you.